Hey everybody, welcome back. So now that we know the definition of a group, we have a pretty good toolkit of examples of groups. It's time to start proving some things that are true about all groups. Actually, we started that journey last video by proving the cancellation property. Now, the great thing I should say about proving things in general about groups is that those things are immediately true for every single example of a group. So in one fell swoop, we're proving a statement that's true about addition of integers, or about composition of symmetries of a square, or about addition of integers mod n, and so on and so forth. The first property that we'll prove today is about the identity element in a group. And it's something that actually we've almost been assuming with the language we use, but we should prove it. And that's, we talk about the identity element in a group, but if we look carefully, all that the group axioms say is that there must exist an identity element. So maybe there could exist more than one. In fact, what this property says is no, in any group, there's only one identity element. So I've stated that as a theorem here, and our first task for today will be to prove that theorem. Before we dive into the proof of that theorem, I want to take a moment to make a little proof writing interlude and just talk structurally about how we're going to prove this statement. This is something, by the way, that I'm going to do periodically throughout the course, especially in the beginning, because I know that many of us are still practicing the techniques of proof writing. And so I'll try to highlight and point out those techniques to you when a new type of technique comes up. So here's a new technique. In general, to prove that there's only one of something, here's what our proof writing strategy will be. We'll suppose that there are two of them, but then prove that those two must actually have been equal. In some ways, this proof structure is kind of similar to like a proof by contradiction. This is referred to as a uniqueness proof. So the theorem that I stated on the previous slide that we're now about to prove, I'd say that what that theorem is the uniqueness of the identity element in a group. So let's use this strategy to prove it. So remember, the statement of the theorem was that there's only one identity element. So the structure of the proof is that I'll suppose there are two of them. So suppose E and E prime are both identity elements in the group G. And my ultimate goal is going to be to try to prove that actually E is equal to E prime. Here's how I'll do it. So for any A in G, the fact that E is an identity element means that if I do A star E, I'll get A back again. And also, if I do E star A, I'll get A back again. I'm going to label those two equations 1 and 2 so I can refer back to them. So that's what I get from the fact that E is an identity element, but E prime is an identity element too. And so, it's also true that if I do A star E prime, I'll get A back again because E prime is an identity. And similarly in the other order, if I do E prime star A, I'll get A back again. Now the key observation here is that all four of these equations are true for every single choice of A. And so here's what I'll do. I'll apply equation 1 to the specific choice where I take A to be equal to E prime. If I plug in E prime for A in equation 1, it becomes the statement E prime star E is equal to E prime. Similarly, equation 4 is true regardless of what I fill in for A. And so I can try filling in A is equal to E. And if I substitute that into equation 4, what it'll say is E prime star E is equal to E. So I'm about to have to flip the slide for the sake of space, but what I want you to notice before I do is that the left-hand sides of these two equations that I've boxed in blue are the same. And so what is this saying? This is saying that E prime is equal to E prime star E, but E is equal to that exact same thing. And if two things are each equal to the same thing, they must be equal to each other. Let's write that out. Again, to reiterate what I just said aloud, since E prime and E are both equal to this expression E prime star E, that means they must be equal to each other. So in other words, E prime is equal to E. So what have we done? We started with two different identity elements, but after some argument, we found that they were in fact the same. This is our structure of a uniqueness proof, and that completes the proof of the theorem. We've now proved a uniqueness statement for identity elements in groups, and in fact, there's also a uniqueness statement for inverses. So let me state that as the next theorem. So in more detail, what this theorem says is let G be a group and let A be any element of G, then A has only one inverse. The proof of this is going to follow a super similar structure to the proof that we just did, but I'm going to let you fill in the details of it in your worksheet for today. Maybe a quick comment about this theorem before we look at our last property is that this is something, again, that's been sort of implicit in the notation and language we've been using when we talked about groups. So it's a good thing we're checking it's true. In particular, when we have an element A, we tend to use this notation A with a power of -1, and we'll say that that's the inverse of A. But when we use that word, the inverse, we're implicitly thinking that A has only one inverse. And indeed, this theorem checks that that's true. And so that notation where we write the inverse of A with those symbols is justified. Okay, so one last property of groups for today, which is a property about how inverses interact with the binary operation. This theorem says, let G be a group and let A and B be any two elements of G. Then if we look at the element A star B and ask, what's the inverse of that element? The answer is that it's B inverse star A inverse. Note that the order changes here. This might be something that you remember from calculating inverses of matrices in linear algebra. But let's check now to make sure that it's true in any group. A surprisingly helpful first step here is to just restate with some more words what it is that we need to prove. So we need to prove that B inverse star A inverse, that was the right-hand side of the equation above. We need to prove that that's the inverse of A star B, right? That's what the left-hand side was, just with a little bit more words. But now, what would it mean to prove this? What does it mean in general to prove that something is the inverse of A star B? It means that that something, if we were to multiply it by A star B, we'd get the identity. And the same is true if we take that something and multiply it by A star B on the other side. So this is what it means for something to be the inverse of A star B. And what we're claiming is that B inverse star A inverse does the trick. That's something we could fill in here that would make these two equations true. So now we've got our work cut out for us. Those are the two equations we need to check. Let's check the first one. So the first equation said that this big expression I've got written up here at the top should be equal to E. So I'm going to break that down step by step to see why that's the case. The first step is to use associativity to rearrange the parentheses. Which leaves me with this expression. And what's helpful about that is that you'll notice inside of these parentheses, I now have B star B inverse, which by the definition of inverses is the identity E. Now the fact that E is the identity means when I combine it with anything else, I'll get that thing back again. You might find it helpful to insert some parentheses here, which is allowable by associativity. So then you can see, oops, sorry, I just noticed I had a couple inverses missing there. So again, now you can see once you insert those parentheses that, oh, I've got an A star E, that by the definition of the identity is just A. And then lastly, by the definition of inverses, I can combine that A with an A inverse to get the identity. So I've successfully proven the first of the two equations I wanted to prove. The proof of the second one of the two equations on the previous slide is super similar, so I won't go through it here. So with that, that's all for that proof. And that's enough for today's video, so I'll see you in class.